and this comes from the vertical structure. And the bracket is 0 means that essentially this gives some invariant part of this B acting on W. So in fact, using a theory of vertex algebra, we can see that this is just can rewrite some AB equals 0 for any AW, any N, a non-negative number. And now AZ, I wrote in this way. As homobar series. So this means that the point is this subspace has vertex algebra structure, and this is called Coset, a vertex algebra of W in B. Okay. So very famous example is called GK of Coset. So let's go that Kent Ori by maybe 1986, maybe. I will maybe call GK or Coset. So they first consider K as non-negative integer, and then they consider some LK SL2, that is simple quotient of affine vertex algebra of SL2, and now tensoring L1 SL2, and taking diagonal action of affine SL2, but it factors simple quotient, so we can consider such a commutant. So the result is just, this is some simple quotient of Virasoro vertex algebra. So I wrote this is simple quotient. Algebra of central charge C. So now C is can be written by 1 minus 6 K plus over K plus 2 and K plus 3. So point is this vertex algebra is just a discrete unitary series of representation of Virasoro algebra. So this means that, so this is sometimes called minimal model and very interesting object, and they said that such a interesting minimal model can be constructed by using affine vertex algebra, using Coset. This is a very nice realization. So natural question is, can we generalize this statement for other cases? Or can we find an interesting unitary series using like similar construction? So the answer is yes. And recently, proved by Arakawa, Tomoyuki and Thomas and Andy, so maybe 2019, right? We want to call ACL, right? The first, I want to explain two statements. First, we consider universal one. Universal one is following. So if K plus H check is not non-positive rational number, and now G is not only SL2 but some consider AD E type for any simply laid Lie algebra, then they consider diagonal action on this space on BKG tensor L1G. Okay? So we consider commutant of this diagonal action, and their statement is this is isomorphic to W algebra of G. So that with SL is satisfied this formula. So this is very good because if you consider SL2 case. This is universal Virasoro algebra. Universal one. I will write superscript C. This is universal one. And C is now minus 6 L plus 2 over L plus 1 squared. And if you apply this formula for L, you get same central charge. Okay? So, and they also using this universal statement. They also get simple quotient version of this statement. So their corollary. So now we take K is admissible levels, and still G is ADE type. Then we consider a simple quotient of universal fine vertex algebra tensoring L1G, that's an integrable representation, but this diagonal action also factors simple quotient of K plus 1, but this is also admissible level. And now consider commutant. The result is simple quotient of W algebra. This is just simple quotient. So I want to explain this. So in Lanzen's notation, he wrote GKF, but our case, we should choose F is just a principal nilpotent. This is our W algebra. Principal. And SLN case, principal is corresponding to partition is just N. Okay. So point is, this gives this W algebra is due to famous Tomoyuki theorem. This is C2 cofinite at Wallis and rational, and this gives a minimal series of W algebra and so nice generalization of GK of Coset. And this contains lots of, this is just a generalization of previous result. For example, I want to explain some Katsuwaki-Moto. Prove this statement for SL2, but of K is admissible level case, and also Arakawa, Ram, Yamada try to prove this statement. For SLN, but K equal 1 case, that is called parafermion vertex algebra, and also Arakawa Jan considers SL3 case, and maybe more. I don't know. So many people try to consider such a statement, but this is something that's nice generalization. But yeah, we want to expect more, right? Because we consider this is just the ADE type. So how about other type, right? This is a very natural question. So today's topic we want to consider B type. Yeah, that's a natural generalization, and we expect. Is there any question? Okay. Okay, so to generalize their statement, we want to, it's better to go back to how to prove their statement, right? To generalize the idea. So I want to explain idea of proof. So essentially, the universal, if you prove universal one, the simple quotient version is essentially only using essentially some property of module and some character computation and so on. In some sense, the universal one is essentially main problem. So the idea is following. So if you consider why ADE type is special, because Frankel-Katz construction So Frankel-Katz construction of L1G means following. So if you take Q, this is a root lattice of type ADE, one of AN or DN or EN, and then we take H, this is Cartan subalgebra of G, maybe identified by Halster, and this is just a complexification of Q. So in this case, we can define pi k. This is Heisenberg-Fock space of H hat. This is some center X to G, some like G, same as G hat. This is center extension of loop algebra of H, and in that case, you can easily define such a Heisenberg-Fock space with highest weight 0. But it is well known that this Fock space has a vertex such a structure and called Heisenberg vertex algebra associated to H at level K. And this level K is a central element acting on the highest weight as level K, complex number K. And in that case, we can define, also if you change the highest weight, it's just lambda for some element Hasta. We can define, this is some also, this is just a pi k module of highest weight lambda, and we want to consider BQ. This is sum of pi 1 alpha. Its highest level is 1 and the highest weight just alpha. This is pi 1 module. But Frankel-Katz say that this is isomorphic to L1G by the following formula. In fact, BQ is called lattice vertex algebra. So this means that BQ is not only a direct product of pi 1 module, but also this itself has a vertical structure by some vertex, some highest weight alpha goes to some E alpha v. This is, so we only need to decide what the corresponding field for highest weight vector. Some E alpha is some has the following form: some exponential, some negative, times exponential, and positive and the same. And S alpha is a shift operator acting on the highest weight vector to some plus minus is determined by a lambda and alpha, but shift plus alpha. And also S alpha is characterized by some any Hn is commute with n equal 0. H is element. If Hn is the element of the H hat. So this defines, this satisfies some vertex algebra action and satisfies some locality and so on. And Frenkel-Katz consider affine real algebra action. It means we need to determine the action of E alpha, H alpha, F alpha by E alpha Z, E minus alpha Z, using this vertex operator. And this is well defined if level is 1. And they show that this is isomorphic to just the integral representation with highest weight 0. So using this nice vertex structure, that nice realization of L1G, algebraic ratio shows that there exists some embedding mu of commutant of Vk plus 1G inside Vkg tensor L1G inside commutant. Oh, this is just a diagonal Heisenberg action tensor Vk. And this is identified with L plus H check. I mean, this commutant is just this PQ is just a direct sum of Heisenberg module. And this commutant may be cutting lattice part, and the remaining part is just Heisenberg algebra. So this says that our commutant is embedding inside the Heisenberg algebra, and such that this image of mu can be characterized by some kernel of operator. And this is some SI. And this SI is formed like some E minus L plus H check alpha I 0 is the coefficient of this kind of lattice type vertex operator. And this is called screening operator. But this description is well known that isomorphic to W free field realization of W principal W algebra, so can prove this statement. So point is L1G has nice free field realization using Heisenberg and can show such an embedding and has nice characterization of screening operator. This is idea. So this means that if we find nice integral representation that has nice such a Frenkel-Katz type realization and get possibly compute such a commutant. So how about B type? In B type, we have no Frenkel-Katz type construction. But so B type. We have spinor representation. In the vertex algebra sense, we consider 2n plus 1 free fermion, the vertex superalgebra. This has this top space looks like just a spinor representation of SO2n plus 1, and this is natural chiarization. And in fact, this has level 1 affine SO2n plus 1 action, and can be decomposed to L10 plus L1 with pi 1. Pi 1 is first fundamental weight, and this just even decomposed to even part and auto part. So really nice. So now, instead of L1G, we try to use this F2n plus 1 and consider commutant. What we get? For theorem, and Thomas and me, and also Thomas has different proof of this statement in the different idea by Andy, but anyway, if K plus H check for SO2n plus 1 is not non-positive rational number, then commutant of diagonal action for Bn inside Bn tensor F2n plus 1. So this is isomorphic to natural expectation is W algebra type P that we use the super algebra. So this becomes not just W algebra of type P, but W algebra of type super B type. That is OSP 1 to n. If the relation is 2 times L plus H check for OSP 1 to n equal K plus H check B plus 1 K plus H check B. And H check B is Dirac-Coxeter number of Bn is just 2n minus 1, and H check is OSP is just a Dirac-Coxeter number of OSP 1 to n is just n plus half. This is theorem. The proof is same. My contribution is the last part. You also construct the same embedding, and this description can be identified with such a W super algebra. The other approach is called using some two-parameter family of W infinite algebra. So in that case, so Andy considered this type of algebra, but taking invariant part of the using changing parity. This induces invariant parity, but this is just maybe called even, only has even conform. This generator has only even numbers. So in that case, this algebra can be realized even two-parameter family of W1 plus infinity, and they consider extension and can prove some characterization. But yeah, yeah. But point is, my construction is compatible with the composition. So this means that sum for lam for mu in P plus for B type, we consider Bk for Bk lambda, Bk mu, tensor, F2n plus 1, can be has nice decomposition of lambda, P plus B type, Bk plus 1, lambda, sorry, tensoring, W OSP, some lambda mu. So we know that such a formula and identified with multiplication space by using, for example, character computation, implied participation, and top spaces, and so on. So okay, evaluation. No, what is next? Okay. So now we want to go to application part. So we go to application. It's a little bit fancy application, I want to say. So first we want to consider some difficult vertex algebra called CDO. It's just a Euler differential operator algebra. It's just called CDO. People like to write just a D, G, K, Euler. You want to write here? On G, sorry. Thank you. Usually G is taking some compact Lie group. So what is the definition? Definition is just induced representation, just a fine vertex algebra case that induced from some trivial representation, but in that case also induced from G hat tensor U GT plus CK acting on some regular function of arc space of G. But I don't want to explain what it is. But instead of explaining this, I want to say that this has a nice decomposition of this formula, pk lambda tensor el lambda star. As a pkg tensor elg with k plus l equal minus 2h check. So this means, and yes, we need to assume that k is generic. So this means that if we take k is generic, there exists, if you consider such a direct sum of module, and point is this has a vertical structure. This means that we have some, there exists some vertical extension of BKG tensor VLG satisfying this condition. Okay? So now we want to consider equivariant W algebra. Essentially, I want to say, first of all, we've considered such a direct sum of this module, and we want to point out that this has some vertex structure. That is all I will use, so we may forget the other things. So in fact, WKGF is defined by some cohomology associated to F on affine vertex algebra, and if you consider principal case, we associate principal, Greenfield so-called reduction. I will just write HDS PKG, and we consider Greenfield so-called reduction of this CDO on G, and that we denote by, that we define to be equivariant W algebra. As a decomposition, it just looks like H Green Sokolov for PK lambda tensor PL lambda star. Okay. So our claim is that some, maybe please prime OSP 1 to n acts on W SP to n, level K tensor F to n plus 1. This is plain. So I want to explain the reason. Just a combinatorics of Mayer's theorem and decomposition of this statement. So I want to explain. So we first consider SP to n, K tensor.
Sorry, Naoki?
Yes.
Are you taking, so this German topological reduction is with respect to principal impulses on the GK side?
Yes.
Is that okay?
Left side. Okay? Okay.
It's all right. Thanks.
Yeah, it makes sense. So, yeah, we can consider this one. So this isomorphic to lambda p plus h ds p. I want to write c here. K lambda tensor VL C lambda star tensor from F to n plus 1. And we have Feijing-Flenger duality. Yeah, I should explain this first. This is some duality in principal W-algebra. Its statement is WKG is isomorphic to WL Lagrange of G. Where LG is Lagrange dual of G, and K and L is related by this formula. And R check is Lacing number. That's used in the definition of admissible level. It's just taking 1, 2, 3, corresponding to ADE, BCF, and G. And H check is Dirac number, and LH check is Dirac number of Lagrange dual of G. So using this isomorphism, we may identify with this module some different level for type B and changing some lambda tilde. Because now principal W algebra of type C is isomorphic to principal W algebra of type B. So we may identify this. And I want to change the position, okay? And also, we use some translation of W algebra. It is motivated by result of Arakawa, Krutik, and Feijing, but essential idea is Greenfeld Sokolov reduction M tensor L is isomorphic to M tensor just L. So, and L is, so if L is integrable. This is idea. So this implies that we can write Greenfeld-Sokolov reduction of VK prime, very complicated. Just F2n plus 1 can be inside of Greenfeld-Sokolov reduction and tensor some lambda star. But this is diagonal action on Greenfeld-Sokolov reduction. So this means using our theorem, say that this is Greenfeld-Sokolov reduction of K prime plus 1 in here, some mu tensor. You can find OSP here, some L prime. Oh, we find OSP. Very long time computation. But yeah, this contribution is our theorem. Anyway, we find the action of principal W algebra of OSP 1 to n. Make sense?
What is commutant?
What's this?
What is commutant?
So yeah, that is our theorem. So if K is generic, then we want to consider of a commutant of this action of principal W algebra of OSP 1 to n inside SP 2 n or level K tensoring F 2 n plus 1 is, what is this? This is just affine vertex algebra OSP 1 to n. So we get affine OSP 1 to n as coset of this some very big vertex algebra. Yes, in fact, this suggests this contains such a Greenfeld-Sokolov chiral equivalent algebra or some chiral algebra OSP is contained such algebra and realize it. Yeah. So that now we consider corollary of this theorem. Okay. So we have this decomposition necessary one, and now commutant. Commutant means we remove this part, right? Commutant means essentially remove this OSP part. What is the remaining part? Remaining part is just some affine SP2n and some module of principal W algebra of B type or some principal W algebra of SP type that is related by Feigin-Plankett law. Yeah, so this implies affine OSP 1 to n has decomposition of lambda level L K SP tensor some L. Maybe also can write SO and SP same, so can write lambda. Or just if you consider module, this is OSP some mu, this just like some lambda. So using this statement, so this explains what is multiplicity space of coset of SP inside affine OSP, right? This gives nice application as the following. Our theorem is, now take K is admissible level for SP to N. Then, if you consider simple quotient of affine OSP1 to N, this is LK SP to N tensor WL SP to N module. Yes. In fact, we use some technique of Bardesserter tensor category. So it was, I have no time to explain it, so I'm sorry. Yeah, it's very need some techniques using induction function. It factors not necessarily non-trivial K and so on. But yeah, this L is related by K plus H check C type and L plus H check C type equal to. And the second statement is, so now we take mu, this is some pk and q, this plk, this is a set of admissible weight for level k, and we consider intersection for root lattice. We consider lk mu. For OSP, we have the composition for lambda. Here K is K for SP lambda tensor W SP, LSP lambda mu, where WLSP lambda mu is Greenfeld-Sokolov reduction of maybe spectral flow of simple module. That is simple module of W algebra of SP, and it's used in Tomoyuki's Edward paper. Maybe I don't have much time to explain this. So, and the third statement is LK nu OSP. So I'm taking this one. This is complete list. Complete list of simple inequivariant and equivalent ordinary module of LK OSP. And the last statement is the category of ordinary LK OSP 1 to N module is semi-simple. It may be known, it is known by Tomoyuki, but we have more. We get rigidity. Maybe this case known by Gorelick-Selganova. But anyway.
So this case is rational? So when K is announced to the first being,
Not
so
rational.
K is, for example, in integer.
Yeah, integer case, yeah, yes. But
This is rational.
yes. Yeah, but in general, not. In general, not. If you restrict the ordinary module, we get semi-simple.
It's quite easy.
I think so. I didn't check that. And I have no time, so just say that corollary. The semi-simple in category of LK SP2N module is also semi-simple and rigid as a corollary. So, sorry, I will stop. Thank you.
Any questions or comment?
So this K is this for SP?
SP,
Not for OSP.
not OSP.
And if we have a disciple for SP, then we can always get such result of OSP.
I think so, yeah. Yes. As a statement?
But you commented it's not rational in general, this part 4.
Yeah, I didn't check, so.
Oh, but what goes wrong? Oh, so for example, for integer levels,
Integer
positive
level
integer
rational,
levels,
yeah,
it's rational? Yeah,
I think rational.
okay.
It's extension rational.
Yes.
Ah,
Yes, because if there, yeah.
oh, okay.
Yes.
Any other question? So this rationality when K is integer is new or
I think not new.
it's not new?
I think it has been proven a triarity paper by Andy Linshaw for integer case, but at measurable case is sometimes new to get such a, and rigidity yes, is new.
Okay, so if there's no other question, let's thank the speaker.